Hello everyone, I'm Shunsuke Kurosawa from Tohoku University, Japan. Today, I would like to show you the scintillation property of gadolinium-gallium aluminum garnet GAGG transparent ceramics prepared by the spark plasma sintering process. Before our presentation, I would like to show you our activity in center. In the laboratory, we grow the single crystal halide and the oxide one for the scintillation material. Also, we prepare the transparent ceramics and the utility scintillator. And these samples are applied to the medical imaging and basic physics experiments such as the dark matter search and double better decay experiment. And in these times, we focus on the transparent ceramic scintillation material. Let me show you the background of our works. Scintillation material needs a high effective atomic number and high density to obtain higher detection efficiency for gamma ray. Here, some conventional scintillation materials are included lutetium, because lutetium has a high atomic number, and lutetium oxides such as LSO or LiSO has a high density. But this sample has a large gamma ray intrinsic background due to the lutetium 176. And this background regarded as noise is big issues for medical imaging, and we focus on hafnium because hafnium has a high atomic number of 72 and no intrinsic background. However, hafnium oxide have a high melting temperature, more than 2560 degrees Celsius. And conventional crystal growth techniques such as Kurashima process, Kurashima process, and microperiodal method are not available for such high melting temperature sample. Skull melting process is available for such oxide, but this method needs a large amount of starting material, and it takes so long time to grow the crystal. So the skull melting process is not suitable for material search, because the material search required quick crystal growth. So we focus on ceramics, because we can obtain the ceramics with a lower temperature with a fast growth compared to a single crystal, and this is suitable for the material search. Especially spark plasma sintering (SPS) is very suitable for the material search, because it's very simple process compared to the other ceramics fabrication techniques such as heap and fast growth. The left side is a schematic view of SPS fabrication, and we operate at high pressure and pulse current and obtain the sample. And the right side, this is schematic view of a strategy of our material search. For lower melting temperature one, we grow the single crystal by the microperiodal method, microprinting method, we can obtain the one crystal a day. So after optimization of element or condition, we grow the large size and high quality crystal by Chokorowski or Kurashima method. Like this, for high melting temperature one, we grow the transparent ceramics by SPS. After the optimization, we obtain high quality ceramics by heap or high quality single crystal by skull melting process. Here, there is one question. Is SPS is suitable for material search? I mean that can we obtain the some sample which can evaluate the light up to decay time using SPS method? So we test the scintillation property for the sample fabricated by the SPS in this presentation. So in this study, we focus on the gallium aluminum granite GAGG because the GAGG scintillator has a good scintillation property. For example, the light out has around 6,000 photon per milli and good energy resolution and no hygroscopic nature. Many researchers has studied on the scintillation property or crystal growth of GAGG, not only single crystal but also the ceramics, transparent ceramics. The GAGG single crystal has a segregation, and the right graph shows the decay time versus the position among the one single crystal. And due to the segregation for serum concentration or another element, the decay time has been changed from a seed side and the tail side like this. On the other hand, the ceramics has a uniform serum concentration, and the decay time or another scintillation property is uniform compared to the single crystal. In this study, we fabricate GAGG transparent ceramics by SPS using this machine. And before the SPS sintering, we operate the pre-sintering under this condition. After the pre-sintering process, we check the single phase of the particle, and also using SEM image, we observe the particle size. And this graph shows the particle distributions, and the average of particle size is around 2.5 micrometer. Here, this is the photograph of ceramics prepared by SPS, and we succeeded in obtaining the large and the transparent sample right here. And using SEM image, we found that the grain size of SPS sample is around 30 micrometers. Here, let me show the transmitter spectrum. Fortunately, the sample has not good transparency, but around the emission band, the transmittance was around 10%. And emission excitation spectra were obtained like here, and the quantum efficiency was around 50%. Compared to the single crystal and the ceramic sample prepared by HIP, the emission and excitation were the same wavelengths. On the left side, this is scintillation light-out evaluation, which means a pulse height spectra, the count versus MC channel, using that setup. And sample compared to the BZO crystal, the GAGG SPS sample had not good light out. And the right side is decay profile, and the decay time was around 120 nanoseconds, and this is lower decay time compared to the conventional GAGG crystal. And so the low light out and long decay time was due to some defect or the trough site, we thought. So we evaluate the thermoluminescence using the synchrotron facility in Japan. And using this process, we measured TL luminescence. The left side is the SPS sample, and the black one is a single crystal grown by the Chokrovsky method. And here, the transparent ceramics sample has an additional peak here and here. And this peak would indicate that new trough site or a defect were generated, and these troughs might be suppressed light output or decay time. Okay, so let me summarize our talk. We prepared transparent ceramics, GAGG ceramics by SPS, but the SPS sample had a lower transmittance, light output, also the energy resolution, and longer decay time compared to the single crystal by Kurashima method and the transparent ceramics by HIP. The reason of the low quality of SPS sample might be some generation of trough from oxygen frequency or the defect, because the SPS is very quick or fast fabrication, so it is easy to generate some defect or oxygen frequency. But despite the SPS sample, we can evaluate the light output. Thus, the SPS is available for very quick material search. And as a future works, we prepared some new material, including hafnium oxide 1 by the SPS. Thank you for your kind attention.